All right, all welcome back to Agonize. So Padma, are you ready to give your talk?
Yes.
Fantastic. All right, in that case, we're very pleased to have Padma Srinivasan talking about conductors and minimal discriminants from hyperelliptic curves. And Padma is currently located at the University of Georgia. Padma, take it away.
Yeah, thank you, Daniel. It's nice to virtually be in the same room with all of you. I think it's going to take some getting used to for all of us to meeting this way. So there is Daniel did not announce this, but if you haven't seen this already, there's a Google Doc where you can post ongoing questions. I will try to pause every few minutes or so to collect questions. It's harder to keep track of what questions people have when you're writing and looking at your slides. But hopefully there'll be room for lots of feedback. Please ask lots of questions. I don't have a little animal in my room to keep your attention, but here are some pictures. So my talk's going to be about conductors and minimal discriminants. I just want to give an overview of what this talk's going to be about. So the main player in this talk too will be a degenerating family of curves, just like in one lens, but I'm going to focus on special curves, so hyperelliptic curves. These are curves with an explicit equation of the form y squared equals f of x. So the simplest kind of curves you can write down. So here are the two pictures at the bottom of the screen. Here are examples. Yes, number theorists, arithmetic geometers know and love, a family of elliptic curves. So for most, the parameter for the one parameter family of curves in this picture is t. So for most values of t close to 0, but not 0, you get a nice smooth curve. But when you plug in t equals 0, the curve degenerates and becomes singular, right? So the main question we want to ask is, how fast does this family degenerate? Is there a way to quantify how quickly the family degenerates on a scale of 0 to infinity, right? So an integer measure of degeneracy, and that's exactly what conductors and minimal discriminants are. The main difference between these two is that one comes from studying explicit equations for the family of curves, like the equations you see at the bottom of the screen. So that's the minimal discriminant. So if you have explicit equations, we can actually do computations fairly quickly. I give you a definition in a few minutes, but that's where it comes from. The other option is to actually study the geometry or the topology of the degeneration, right? And that's, oops, did my screen disappear? Or do I just not see it?
Looks like it disappeared.
Uh-oh.
You want to click screen share again and see if you can?
Yes, I don't know why that happened.
I'm sure this won't be the first technical issue.
First hit. Okay, thanks. Right, so the discriminant comes from studying equations for the family of curves. The conductor more closely reflects the topology or the geometry of the degeneration. And it's hard to read or see the geometry from the explicit equation, so it makes the conductor a little harder to compute. But it's the invariant we'd like to understand better, right? So a natural question at this point is, if you have two ways of measuring degeneration, one that you can actually compute and the other that you like to understand, it's natural to ask if there's any relation between these two numbers, right? So that's the main goal of this talk. Why should you even expect such a relation? So for this, this goes back to Tate in the 50s when he came up with Tate's algorithm for resolving singularities, for writing down the minimal regular model for elliptic curves. He observed as a byproduct of his algorithm that these two different ways of measuring degeneration are actually equal when the genus is 1. And his computation assumed that the residue characteristic is not 2 and 3 to stay away from issues of coming from wild ramification. So then in the 60s, Ogg realized that you can extend Tate's equality to small primes if you throw in a correction term to account for wild ramification. And but his argument had a little gap in the mixed characteristic 2 case, and that took another 30 years. But late 80s, Saito settled this. So And for genus 1 curves, these two invariants, these are actually equal on the nodes, right? So the next reasonable case is to go from genus 1 to genus 2, the same equally stepping up the degree of the polynomial f in y squared equals f. What Qing Liu saw in this case is that these two invariants, these two numbers can be different for genus 2 curves, and he showed explicit examples where they're not equal, but he observed that there is an inequality. Not all is lost. You can prove that the conductor is bounded above by the discriminant. So natural question is, okay, we've done genus 1, genus 2. What happens if we now, what happens to hyperelliptic curves of arbitrary genus, right? So that's the main goal of today's talk. In earlier work, I managed to show that the Qing Liu's inequality extends, assuming the residue characteristic is larger than 2g plus 1. This is similar to Tate's hypothesis. You can see that in genus 1 just means assume the residue characteristic is not 2 or 3. This implies there's no wild ramification. But for today's talk, we will actually deal with wild ramification, the thing that people never talk about, but today we're going to be brave, and we're going to embrace wild ramification. With joint work with Andrew Obus, we managed to show that Qing Liu's inequality holds as long as you assume the residue characteristic is not 2, right? So that's the main goal for today's talk. So the plan is I start with recalling definitions of these invariants, and then I'll actually compute them. We compute them together in some examples, and then use these examples to motivate the general strategy for proving such an inequality. All right? Any questions so far? Is the setup, is the goal clear? 4 new messages. Okay. All right. I don't see anything in the chat. Okay, so let me set up. If there are questions, maybe Daniel will unmute himself and ask me. But okay, so let me go set up. Okay, great, excellent. So let's actually set up some notation for talking about families of curves. We need the 1 parameter base for a family of curves, so that's going to come from a nice complete DVR with fraction field k, right? The usual suspects. The residue field is going to be little k. The invariants I study don't change when I make unramified base extension. So from the very beginning, I'm going to assume the residue field is algebraically closed. And like I said at the beginning, we want to stay away from characteristic 2, right? And then you have an algebraic closure, the Galois group, the valuation, and so on. For the rest of the talk, if you want to keep a concrete example in mind, you can take K to be the power series ring, like 1 and dead, with the Riemann series field, the fraction field of the power series ring. Or if you like QP better, you can take the maximal and ramified extension of QP and the ring of integers in there. All right, so all of this sets up the base, and then what we want, like one line, we want a nice smooth hyperelliptic curve over the punctured disk over K, right? And G is going to be its genus. So what's the minimal discriminant? Like I said, this comes from writing down an explicit equation, right? Remember, our curve's hyperelliptic. We need to make good use of this fact. So a hyperelliptic curve comes with an equation, y squared equals f of x, right? We started out with the curve over K. This means the equation a priori has coefficients in K, but if there are any t's in the denominator, we can do changes of variables to clear out all the t's. So we can look at integral equations, so equations where the polynomial f has coefficients in OK. So what can you do with such an equation? Our goal is to make an integer that measures degeneration, right? So from the polynomial f, we first make an element of OK by taking the discriminant of this polynomial, right? That gives you an element of OK. And if you have an element of OK, you take its valuation to make an integer. Right, so that's the discriminant. The only problem with this is that the same curve can be defined using many different equations, right? You see an example on the slide. C1 and C2 are actually the same curve, same family of curves over the punctured disk, and you see an explicit change of coordinates that takes one curve to another. But this number that you compute depends on which equation you start out with, right? So we want an invariant that only depends on the curve. And one way to get rid of this dependence is to write down all possible equations, compute all possible numbers, right? These are all non-negative numbers. You take their minimum, right? They're all bounded below by 0. In this example, you haven't, the second equation is actually a trick question. The second equation actually describes the constant family, right? There are no t's. And this has good reduction, right? So the main reason this minimal discriminant is a measure of degeneracy is because it's 0 exactly when the family of curves does not degenerate, right? Like the second equation C2 shows that there's actually the constant family. There's even the central fiber is smooth, and that's reflected in the minimal discriminant being 0. This might be a little confusing to number theorists. I've been told I should always warn people. What I'm talking about is the valuation of what we usually call the discriminant in number theory. So I'm fixing a prime, and I'm looking at the p-adic valuation of the discriminant, right? So order of the minimal discriminant in my sense being 0 means the usual discriminant is a unit, which means you have good reduction. Yeah, this is good. Any questions in chat? I don't see any questions in chat. Okay, so that's all I had to say about the minimal discriminant. Let's move on to the conductor. Like I said, the conductor comes from studying the topology or the geometry of the degeneration. So if you want a number that reflects the topology of the family of curves, you look at the Euler characteristic, right, of every curve in your family. And the Artin conductor, what it is it's basically the difference in the Euler characteristic of the generic curve in your family and the degenerate curve when you plug in, when you look at the reduction. The only thing here is just like with the minimal discriminant, you had to look at wire stress equations, single equations with integral coefficients. The thing that you need for talking about the Artin conductor is what's called a regular model. I give you examples in just a bit. This just means that even if your special curve in your family is singular, you can make sure that the total space of the family of curves, this is some surface, that's nice. All the tangent spaces are two-dimensional, right? So the total space of the family of curves is regular, but fiber it, maybe you get something singular. Here again, there's a problem, there's a choice. There isn't one proper regular model, model for the curve. There are many, and just again, to get rid of the dependence, to have a well-defined invariant, there's one that's special. There's one called the minimal proper regular model, right? The difference, the Weierstrass models have the advantage that they're given by a single equation. This minimal proper regular model, it's given by a bunch of equations with coefficients in OK, but maybe this embedded in some huge dimension projective space, right? It's hard to explicitly work with, but it exists. And the Artin conductor basically records the difference in the Euler characteristic of the generic curve and the special curve. At this point, you should stop and ask me, what do I mean by Euler characteristic? If we're working over something like QP, your reduction is a curve over FP bar. So what does it mean to talk about the Euler characteristic of a curve over FP bar? There is one, you take the et al. Cohomology, right? This agrees with, if you're over C double parenthesis T, this is good old singular cohomology by comparison theorems, but all we need is a good cohomology theory that reflects the topology, right? So we work with the et al. Euler characteristic. That's the definition on top of the slide. So that's basically it. That's what Tate worked with. And this little delta here is the correction term that Og had to add in for primes, for small primes, right? It's what's called the Swarm Conductor for the Galois representation on et al. On the first et al. Cohomology group. It's a non-negative integer, and it's 0 most of the time. It's 0 when the residue characteristic is larger than 2g plus 1. Right? But if you're working with small primes, you do have to correct for it, and it's some measure of wild ramification. I will give you a working definition of the Swarm conductor in just a few minutes. It looks scary, it says wild ramification, but we can actually compute it for hyperelliptic curves. All right. The discriminant was fairly straightforward. The Artin conductor might be a little more unfamiliar, so I thought I'd record some nice facts about the Artin conductor. The first is that, okay, we had to pick some auxiliary prime to talk about étale cohomology groups, but this invariant doesn't depend on which auxiliary prime you choose. The main thing, if there's one thing you take away from this talk, it should be that conductors and discriminants are measures of degeneracy. They are 0 exactly when the family of curves extends smoothly over the puncture, and it's in general some non-negative number that measures how bad the reduction is. Some other ways you might have of measuring degeneration, and another thing is to see how many pieces the curve breaks up into when you degenerate, right? So the Artin conductor of X is related to the number of components in a degeneration. It's the number of components minus 1 plus the delta you saw in the previous slide plus an epsilon. This epsilon is the tame conductor for the Galois representation on H1. In number theory land, we quite often see the conductor that shows up in the functional equation for an L function. That's just the bit coming from epsilon plus delta. That's an invariant that picks up whether the Jacobian of the curve has good reduction, right? There can be families of curves, like families of genus 2 curves, where the family of curves has bad reduction, but the associated family of Jacobians has good reduction. Right? In that case, epsilon plus delta will be 0. So that's not good enough for us. So we have to add in a little correction coming from the number of components in the special fiber, right? So that's another way to think about the conductor. If you're an algebraic geometer, maybe you'd like to ask what is this really measuring when you have semi-stable reduction over the ground field. In that case, the Artin conductor just counts the crudest measure of degeneration, which is just count how many singular points you have on the special fiber, right? So that's what this is. But you might not have semi-stable reduction over the ground field, and I want an invariant that detects good or bad reduction over the ground field. So it's in general, it doesn't have a straightforward interpretation like this. Is there a question?
Can I ask you a question? Yeah. This is Ravi here. So partially just a question that might just slow you down a bit to ask some questions. So are all these properties are in conductor, and it's not obvious to me which ones imply. I mean, it's not obvious that much of these are not obviously related to each other. So I should just take all these as just facts which are true, or should they somehow be?
These are facts that are true that you can derive from the fact that it's the difference in Euler characteristics of the generic and special fiber. You have to throw in a bunch of other ingredients
so it's
base change. But for now, I'm just trying to give you different ways to think about it. You can pick your favorite one. Great. And I have a favorite one that I use for computations that I'll talk about in a bit, but I just want to make you feel comfortable thinking about this invariant. It's something you've seen before.
Thanks.
Thank you. Great, thanks for slowing me down. This is great. Are there any other questions?
There was a question posted on the Google Doc and then deleted, but I think it's a good one. So is it all right if I ask it? So the minimal discriminant relied on having an explicit equation for your hyperelliptic curve, right? And there are other families of curves which are defined by fairly explicit equations, like plane curves or something. And the question was, are there other notions of minimal discriminants in those other sorts of situations?
Probably is. Right now, I'm working on a project with Andrew to, the simplest extension is to look at superelliptic curves, right, or the cyclic equations. What we're really using here is that the curve has a map to P1, and we're trying to use the degeneration of this map to cook up an invariant, we're measuring the degeneration of the branch locus. You can totally do that. You'll have to adjust it. In the superelliptic curves case, it's the main theorem is not just conductors less than or equal to discriminant. You have to correct by a factor coming from the degree of the cover.
Great, thank you.
Great, great questions. Is there anything else? Any other questions about the definitions of these invariants? Let me put up the main theorem again. So I've given you many different ways of thinking about the Artin conductor, but the definition I'll use is that it's the difference in the Euler characteristic of the generic and the special fiber plus a correction term for Weil ramification. So the main theorem is that this invariant coming from topology is bounded above by the discriminant, minimal discriminant, which comes from explicit equations. Is the statement clear? Any other questions? Should I go on, Daniel?
Yes.
Okay, excellent.
Well, Ravi still raised his hand, but Ravi, do you have a question or?
Sorry, that was my actual earlier question, which I interrupted.
Okay.
Great, sorry.
Yeah. Yeah, so you could think about how to get these other definitions from the main one, but like don't do it now, like it might be distracting. But you can derive these from the main definition. The definition that's most useful for computation is what I have up here, the difference in Euler characteristics plus Swarm conductor. All right, are you guys ready to compute the conductor? Yes, I say yes on behalf of all of you. Let's actually compute this invariant. It's maybe scary looking with the Swarm conductor, but we can do it for hyperelliptic curves. All right, so the third section of my talk. Can you all see my screen? Yes. So some tools for computation. Right. We want to compute these invariants and prove an inequality. So let's tackle the scary one first. Let's talk about the Swarm conductor. Right. So like I said, it's some invariant that measures wild ramification of H1, but the main thing we're supposed to remember is that this is not some crazy old curve. This is a hyperelliptic curve, right? It's given by an explicit equation y squared equals f. I must say that for the rest of this talk, I'm going to pick an equation that attains the minimal discriminant. So when I say f, I mean the f for which the valuation of the discriminant of f is the minimal discriminant of the curve, right? So a hyperelliptic curve has such an equation, and we should, whenever you see a hyperelliptic curve, and you want an invariant associated to it, you should ask, how can I read this off from the polynomial f, right? So the first thing to observe is that the roots of the polynomial f give you two torsion points on the Jacobian of the curve x. And the two torsion on the Jacobian is the same, it's a quotient of the Tate module. The Tate module is like homology. It's dual to the cohomology of the curve. So the roots of f are actually giving you a piece of the Étale cohomology of the curve. Okay, to be completely correct, I need to put in a dual, right? So if you want to understand the action of wild inertia on this piece of the Étale cohomology, that's the same thing as understanding the Galois action on the roots of f, right? That's something we study in algebraic number theory all the time, right? So we want an invariant that picks up the action of wild inertia on the roots of f, right? So to write down a formula for this invariant, let me first write down an irreducible factorization for the polynomial f. Once you have this, you also get all these field extensions of your ground field, right? So the Swarm conductor for the action on Étale cohomology is, okay, and also remember, like we assume that 2 is not the residue characteristic. That's why I can look at the Galois action with z mod 2 coefficients instead of z2 coefficients. I can work with this instead. So what I want to understand is Galois action on the Étale cohomology, scary looking thing, the same thing as the Galois action on the roots of f. So that's just a permutation representation, right? And so the Swarm conductor for this Galois action, there's this action on the roots of f breaks up into many different orbits, one for each factor, right? And we want to understand the Swarm conductor for this permutation representation. If you go look in Serre's local fields, the scary looking, I haven't told you what, I mean, the Swarm conductor is something you attach to any representation of wild inertia. But in this case, when you're just looking at the action on the roots of a polynomial, in Serre's local fields, there's this thing called the conductor discriminant formula. It says that this is something you can read off from an invariant we all learn in algebraic number theory, namely the discriminant of the field extension. It's the valuation of the discriminant of the extension ki over k minus the degree of the polynomial plus 1. Right? So in the case of hyperelliptic curves, the Swarm conductor, this scary sounding invariant, is something that you can read off from the field extensions coming from the irreducible factors of f. Right? It's the valuation of the discriminant of the field extension minus degree plus 1. Yeah, so you can actually compute it. It's not scary, and we're going to do this in examples in just a bit. Right, so this is the formula. This is the working definition of the Swarm conductor for hyperelliptic curves. The other thing now we have to deal with is we want a formula for the étale Euler characteristic. And again, we should remember we're not dealing with arbitrary curves. We're dealing with hyperelliptic curves. So these are covers of P1. And if you ask your topologist friend, how do you compute Euler characteristic when you have a cover of curves, they say, okay, you should use the Riemann-Hornets formula. Right. So here's the statement: if instead of if instead of picking an arbitrary regular model, if you have
So Padma, another question, just because there are a lot of deltas running around, just a couple lines above, there's the Swarm conductor. Can you remind me which delta is, there are 3 different deltas in that. One's a Swarm, can you just restate what the various ones are?
Yeah, so this delta sub x on the very left, that's the Swarm conductor that we want, the Swarm conductor for the action on H1 of the curve, right? And because H1 of this curve is the same thing as the permutation action on the roots of f, this is the same thing as the Swarm conductor for when I write delta sub ki over k, I mean the Swarm conductor for this regular representation on the roots of f. And
that's also called the Swarm conductor.
Yeah, yeah. Great. So the Swarm conductor is something you can associate. I should say, I didn't do the most general thing, but for side comment, you can talk about this if you have some GK representation V, you can talk about Swarm V. This is the Swarm conductor that measures how non-trivial the action of wild inertia on V is, measuring action of, or non-triviality, I should say. Oh, I don't know how to fit this in. It's some measure of how non-trivial the action of the wild inertia and actually the whole ramification filtration on V. There's a definition in terms of invariant subspaces, but for hyperelliptic curves, it boils down to this really concrete thing in terms of field extensions. Is that good?
Yes, thank you. Thanks very much.
Yes. Okay. Thanks. Right. So, okay. Takeaway: Swarm conductor for hyperelliptic curve. It's related to discriminants of the field extensions generated by roots of f. Now we have to deal with the étale Euler characteristic. That's something we have tools from topology. So if the regular model X of the hyperelliptic curve actually comes from, if it's the double cover of a model of P1, if it's a normalization of a regular model Y of P1, right? So the point is writing down models of the curve, of a general curve X are hard, but like you try to work with P1 instead. P1 super nice. So if your regular model is the double cover of a model of P1, and and this map of arithmetic surfaces, if this is branched along a divisor B, right? You have a cover of surfaces, then the branch locus for this 2-to-1 cover is going to be some divisor. Then you have, then you can compute the Artin conductor upstairs by working with the model downstairs, the model of P1 downstairs, and the branch divisor. So what was the Artin conductor? It was the difference in the Euler characteristic of the generic and special fiber. The generic fiber and the special fiber are both curves, right? Curves over different fields, but we can apply the Riemann-Horowitz formula for the generic fiber and special fiber separately. What does the Riemann-Horowitz formula say? It says for every point, the Euler characteristics are additive, right? So it says for every point in the generic fiber and special fiber downstairs, you get 2 points upstairs in the model. So you get twice the downstairs Euler characteristic, except over points of the branch locus, right? Minus the Euler characteristic of the branch locus, and add to it the Swarm conductor, right? So here I've talked about the Artin conductor for a regular model. This, like I said, there are many different regular models for the same curve. And for our purposes, all we are trying to prove is an inequality. So the Artin conductor for the minimal regular model is going to be something on the very left of this inequality. So it's enough to produce, for proving an inequality, it's enough to produce some regular model where we can compute the Artin conductor and show that it's less than or equal to the minimal discriminant.
So sorry,
right?
A question, Padma?
Yes?
And I apologize if I shouldn't be interrupting, but I figure no one else.
No, this is great. I mean, I missed questions. Thank you.
Yeah, so the Artin conductor, just to remind me, it is dependent on the choice of the regular. It's not just a function of what's going on over the function field.
No, it's really not a function of the generic fiber. It depends on the model. And,
oh, no, it does depend on the model. Okay, great.
Yes, it's the difference in the Euler characteristics of generic fiber and special fiber of the model. If I talk about the Artin conductor of X, the generic fiber, I'm secretly picking the minimal regular model.
Aha, thanks, great.
And if you remember the formula, I had a list of formulae, helpful formulae. One of them said it's related to the number of components in the special fiber, right? So the minimal regular model has the least number of components, right? So you have an inequality out of the minimal regular model is less than or equal to Artin conductor for any old regular model. The remaining terms, epsilon and delta, only depend on the generic fiber, but the contribution coming from the special fiber is in the number of components. Thanks. Helpful questions.
Thank you.
Yeah. Yes, I really miss questions. It's otherwise it feels like I'm talking to the tree in front of me. So it's helpful to hear voices. Okay, so we have working formulae for computing Euler characteristics. We also have a working formula for the scaling Swarm conductor. Let's actually use these to compute the Artin conductor in some examples. Right? So I'm going to show you 2 examples in this talk, and if we understand these 2 examples well, we can generalize. We can figure out what we need to do for a general hyperelliptic curve. So my first example, let's say I'm working over QP here, and my hyperelliptic curve is going to be given by y squared is x to the p minus p. We call this f. The argument that I'm going to give works for any Eisenstein polynomial, but let me just pick one to keep things simple. Right. So to compute the Artin conductor, like I said, we want a regular model, right? In this case, the equation y squared is x to the p minus p. This is already an integral equation, and you have a Weierstrass model. Right? And in this specific case, the Weierstrass model is the minimal regular model. right? And this is the Weierstrass model. It is the double cover of P1. Right, and the branch locus of this double cover is exactly the curve, is a vanishing locus of this curve, and you also have this component at infinity, right? So if you want to keep a picture in mind, here's a cartoon of P1 over ZP, right? You have the generic P1 over P1 over QP unramified bar. That's your generic fiber. And then you have the special fiber. That's also a P1 in this case, right? P1 over FP bar. And where's our branch locus in this picture? It's this thing that looks like the cuspidal curve. Like when P is 3, it's like x cubed minus 3, right? So it's this curve that's very tangent. And if I want to, the whole branch locus of this double cover also has the closure of the point at infinity, right? So to apply the Riemann-Hurwitz formula, remember what do we need? Let me scroll back up. You need, we understand the special fiber and the generic fiber of the model downstairs. Those are just P1 over FP bar and P1 over QP bar, QP unramified bar. And now we need the special fiber and the generic fiber of the branch locus, right? So the special fiber, if geometrically, it consists of P+1 points, P+1 close points, the roots of x to the P minus P plus the point at infinity. And the special fiber of the branch locus, here's the thing, the special fiber, it taking this equation and reducing mod P, right? So that gives us just one fat point. But Euler characteristics don't care about whether the scheme's reduced or not, right? So this whole P points, the P roots of this polynomial F reduced to a single point. You just get the point over, all reduced to the point 0. And then you also have the point infinity, right? So two close points. And to compute the Artin conductor, we need the Euler characteristic of P1 over FP bar, P1 over QP unramified, and all of these points in the branch locus, right? So here's a question for the audience. Let me try this. I don't know how to call out on one of you out of 100 people, but I just make sure everyone's awake. I tend to ask people, what's the Euler characteristic of P1, right? We want the Euler characteristic of P1 over FP bar, P1 over QP. I mean, it's the same answer. Here's a hint. It doesn't matter which field you're working with. What's the Euler characteristic of P1?
2.
Sorry, well, you should think like a topologist, right? We are measuring the topological Euler characteristic. So you should be thinking in your head 2 minus 2g, right? P1 is genus 0. So you get 2, right? So both of these terms, both the special fiber and the generic fiber have Euler characteristic 2. What about the Euler characteristic of a point, close point, right? Single point, it's 0 dimensional. So if you're doing alternating sum homology, 1. Okay, thank you. So this is just 1. So we can plug everything into our formula, right? So, okay, let me write the formula again. The Artin conductor of X, you want twice the difference in the Euler characteristics of the generic fiber and the special fiber of your downstairs model. Take away the Euler characteristic of the branch locus. Right? Euler characteristics are additive. That's the key defining feature of Euler characteristic. That's what's so great about them. And we can actually compute it here. We just saw both the generic fiber and the special fibers are P1. So you get twice 2 minus 2 minus the difference in the Euler characteristic of the branch locus, right? So a general, I mean, infinity just reduces to infinity, but in the special fiber, I'm going to write it this way. P points on the generic fiber collapse to 1 point in the special fiber, right? So you get a 1 minus degree f. That's the difference in the number of close points. That's the drop in the Euler characteristic here. Plus, let's add in a formula for delta, right? So in this case, you have just one irreducible factor. It's an Eisenstein polynomial, right? So this is kp to the 1 over p over k. And our formula, working formula for the Swarm conductor says, take the discriminant of this field extension, subtract the degree, add 1. Okay, here's my favorite part of the talk where I get to cancel things. You see that this degree f plus 1 cancels exactly with 1 minus degree f coming from the drop in the branch locus. And what you're left with is the discriminant for this field extension, right? How do you compute the discriminant of a field extension? There's even a totally ramified extension. Any suggestions from the audience? 2 factorial 2. Oh, okay, I don't understand the chat. Does someone want to tell me how you compute discriminants of field extensions of a totally ramified extension? Write down a minimal polynomial for what? We need to pick a uniformizer. We need to pick our favorite uniformizer, write down the minimal polynomial for a uniformizer and take its discriminant, right? But here we have a favorite uniformizer, a root of f, right? So a root of f, p to the 1 over p is a uniformizer. For k1, so we can use the minimal polynomial of p to the 1 over p, namely f, to compute the discriminant of this field extension. And voila, we just proved this. We proved the conductor equals the discriminant in the case of an Eisenstein polynomial. Is this computation okay? We proved the conductor discriminant equality for Eisenstein polynomials. Okay, pause, no questions. Okay, let's do something slightly more complicated. Let's move away from Eisenstein polynomials. Here's my second favorite example. It's when the curve's given by x to the p minus p squared. This is no longer Eisenstein, right? What's changed in this example? So this is an example where you actually have to do some blow-ups. The Weierstrass model, the usual double cover of P1 of OK is not regular, right? If you look at the point, what does regular mean? Okay, I skipped saying this when I had slides, but regular means that the dimension of the tangent spaces on this arithmetic surface should all be 2-dimensional. But if I compute the dimension of m mod m squared on the Weierstrass model at the point x equals y equals p equals 0, this is 3, right? What was different in the Eisenstein example was you had y squared is x to the p minus p. So once you had y and x, you got the third generator p for free, right? But that's no longer true. This whole equation is in the square of the maximal ideal. In particular, it's not 2. So the Weierstrass model is not regular. And that's one difference. The other difference is the root of f is no longer a uniformizer of the field extension k1. This is still an irreducible polynomial, but a root of f is no longer a uniformizer. But we know it's no longer a uniformizer for k1 over k. All right, so all right, so these are two things that we know are going to be different, but let's see let's see how to deal with this, right? So if I want to compute the Artin conductor, our strategy is to not directly write down a model for the hyperelliptic curve, to write down a model for P1 first. So the change you have to make in this example is instead of taking a double cover of P1, you first blow up P1, right? You take a blow up of P1. You have to blow, this is a computation that I strongly recommend, especially if there are any graduate students in the audience. You can you can see that if you blow up P1 over ZP P minus 1 over 2 times, you first do this blow up, then take a double cover, this model will be regular. Right? And this is the model we work with for applying the Riemann-Horowitz formula, right? The generic fiber, the geometric generic fiber is still the same. That's not changed, right? What changes when you blow up is the special fiber, right? So the special fiber of this blown up P1 looks like, instead of a single P1, now you have a chain of P1s, right? You have it, you blown up P minus 1 over 2 times, so you have P minus 1 over 2 plus 1 components, right? So if I want to, again, my idea is to try and use the Riemann-Horowitz formula. The branch locus looks the same. Here again, you have 2 close points for B of K, and B of K bar is all, again, P plus 1 over 2 points. P plus 1 points, close points. So the branch locus, the geometry of the branch locus hasn't changed, but the special fiber of the model downstairs has changed. So now we need the Euler characteristic of a chain of P1s. Okay, so and this is you have P plus 1 over 2 P1s. Do you remember how to do this? So how do you know, there's only one way to compute like Euler characteristics when you have an explicit picture, and that's to do inclusion exclusion, right? So how do you build this chain of P1s? You start with a single P1. Every time you blow up, you delete a point in this P1 and stick in glue in a whole P1 instead, right? On the level of Euler characteristics, when you're doing cutting and pasting, like deleting a point is like subtracting 1, and adding in a P1 is like adding 2, right? Every P1 has Euler characteristic 2. So overall, each time you blow up, you do minus 1 plus 2, minus 1 plus 2. So each time the Euler characteristic goes up by 1. So overall, the Euler characteristic of the special fiber is 2 plus the number of times you blow up, number of blow-ups in Y to P1K, right? So overall, the rest of the computation is exactly like in the case of an Eisenstein polynomial. So R plus of this regular model, this double cover of this blown up P1 now looks like 2 times 2 plus number of blow-ups minus 2. So it's just 2 times the number of blow-ups in this model, minus the difference in the Euler characteristic of the branch locus, which is still 1 minus degree F, plus the Swarm conductor, the discriminant of this field extension, minus degree F plus 1, right? And just like before, you have this nice cancellation. You forget the 1 minus degree F, and what you're left with is, in this case, you have to blow up P minus 1 times, right? P minus 1 plus the discriminant of this field extension, right? What is the field extension in this case? The field K1 is Kx mod the defining equation x to the P minus P squared. So it's a field generated by P to the 2 over P. It's the same as the field generated by P to the 1 over P, right? The field itself hasn't changed, so the discriminant hasn't changed. What's changed is that P to the 2 over P is no longer a uniformizer. Root of F is not a uniformizer. But we can see how far off, I mean, we are from, how far off the lattice generated by the roots of F is from being the full lattice of the ring of integers, right? So if I were to compare the discriminant of the polynomial F with the discriminant of the field extension, I still have to use, for computing the discriminant of the field extension, I still have to use p to the 1 over p, right? This is vk of the discriminant of x to the p minus p. We are overcounting when we compute the discriminant, when we use the roots of x to the p minus p squared, right? But we can see exactly how much we are overcounting by. Every time we, the roots of f, what's the discriminant? It's the product of differences of the roots of f. And every time, instead of using a 1 over p, evaluation 1 over p coming from the difference in the roots of f, you're using a 2 over p, right? So you're overcounting by 2 over p minus 1 over p for every pair of roots. And how many pair of roots do we have? We have p choose 2. And in the discriminant, every pair of roots shows up twice, right? The discriminant of a polynomial is product of differences of the roots of f. Every pair of roots shows up twice. So you have this little extra bit coming from the fact that a root of f is not a uniformizer. And how much is this? If you simplify this, this is exactly, magic, this is exactly what you wanted, right? It's p minus 1 plus delta k1 over k, which is the ardent conductor of this model. Yeah, this is computation look good. Okay, I don't see anything in the chat. All right, so the main thing that made this computation work is the extra contribution that we needed coming from the fact that you had to blow up P1 first is balanced out exactly by this extra quantity here, which we call the discriminant bonus of the polynomial f, right? So here's the definition. This is the key invariant we need to understand in general. You can also think of this as a logarithmic co-volume, right? It's measuring how far off the lattice generated by the roots of f is different from the full ring of integers. So the discriminant bonus of the polynomial f, let's say I even pick a factorization, is exactly measuring this difference. I'm going to call it, later on the paper, I call this dbk, db for discriminant bonus. This is the valuation of the discriminant of the polynomial f, take away the valuation of the discriminants of the field extensions. Right? So the key thing that made the previous example work was that this discriminant bonus was larger than, was enough to balance out the number of blowups we had to do downstairs, right? So hopefully I've convinced you at this point of this key that it's enough to do the following. So here's a key reduction step. So to prove the conductor discriminant inequality, it suffices to produce what we did in these two examples. We want to generalize that. So for every integral f, a model, we want to use the Riemann-Hurwitz formula. So we want to produce a model y sub f of P1 such that the normalization, this double cover that you get by taking the normalization of the surface in the function field of the hyperelliptic curve, this double cover of this blown up surface, you want that to be regular. And to prove the inequality, if you expand things out, what you need is twice the number of blowups that you need to do. This needs to be bounded above by the discriminant bonus, right? So this is the kind of thing we need to do in general if you want to adapt the strategy from the previous last two examples. I want to draw your attention to two things. The first is that the main reduction here is that we're now talking about models of P1, not models of X. And these, I guarantee, I assure you that these are much easier to work with. So model of P1, not X, these are much easier to write down explicitly, right? Directly, the reason this problem's been open for a long time is that doing explicit resolution of singularities for higher genus curves is hard in general. Like resolution of singularities algorithms require you to blow up and then normalize and then blow up and then normalize. It's very hard to keep track of invariance. Tate's algorithm turned out to be a little too easy. All he had to do was blow up, but you can't expect that to work in general for higher genus hyperelliptic curves. But what we're doing here instead is, instead of directly producing a model for the hyperelliptic curve, we're instead trying to produce a nice model of P1. And models of P1, I tell you, we have a nice tool for writing these down explicitly. And that's one thing I wanted to say about the strategy. The other thing is, look at this, we gotten rid of the scary Swarm Conductor, right? So there's no delta. This discriminant bonus is this really concrete thing. It's just measuring how far away the roots of f are from generating the full ring of integers, right? So everything is very concrete in this problem. All we have to do is produce a nice model of P1 such that its double cover is a regular model of the hyperelliptic curve, and have some kind of control on the number of blow-ups that you need to do, right? Is everybody okay with the strategy? Daniel, are there any more questions in the Google Doc that you want to ask?
No, I think it's looking good. But maybe
okay.
If we pause for a minute, we can see if anyone wants to raise their hand or type something into chat.
Yeah, this is the main point to stop. So this is the strategy I wanted to convince you of, and the rest of the talk's going to be saying, hey, we can do this. It's a good time for questions. I do not see any raised hands. All right, so, here's the key proposition in our paper. If you're convinced of the strategy, the main proposition is that we can produce such a model of P1 such a y sub of f exists. So if I want to break this up further, what does such a y sub f mean? We need to produce an explicit model of P1 such that the double cover of this model gives a regular model of the hyperelliptic curve. So this, if I wanted to describe what it is, what we need to do in general is an explicit embedded resolution of the divisor of f on P1. The reason we couldn't use the Weier's stress model in the x to the p minus p squared example was we had a p squared in f of x, right? So you can fix the model of the hyperelliptic curve by fixing the divisor of f inside p1 of OK. So you blow up p1 of OK enough to make the divisor of f regular, right? This is something that people knew from a while ago. Like you can produce explicit regular models by doing explicit embedded resolutions one dimension lower. But the main thing is that we want to keep track of invariance, right? The key thing that makes our calculation work is we not just show that such a thing exists, we can actually keep track of how many blow-ups you need to do. We show that the number of blow-ups is bounded above by some quantity that's comes from the explicit way we have for writing down models, and we show that the upper bound we get on the number of components is less than or equal to the discriminant bonus, right? So how do you write down, so these are the three steps in the proof. So how do you write down explicit regular models? You don't want to be writing down a fine patches for a big blow up, right? X to the p minus p squared was a little easy. You don't want to be doing this in general. The key thing we do first is that you can describe models of P1 a different way, right? So every irreducible component in the special fiber of this model gives you a way of gives you a valuation on the function field of P1, right? You can ask, if you're given a function on P1, you can ask what is its order of vanishing along this component. And instead of describing the model using affine patches, what we do is explicitly give you a list of valuations that correspond to the components in the special fiber of this model. So what we do is explicitly write down models of P1, valuations on the function field of P1. This actually is due to MacLean. He did this in sometime in the 1930s. So there are very explicit descriptions of valuations, discrete valuations on this is just K of X, right? Fraction field of a polynomial ring. And this description, it'll take a whole hour to just set up notation to talk about how he writes down valuations, but this is something you can teach a graduate student or even an undergrad. It's just playing around with polynomials. You have an explicit description of valuations on the fraction field of P1, but the main thing is that this description is explicit enough that you can count. You can count bound the number of blow-ups. And I just want to tell you the shape of this upper bound, right? Bound number of blow-ups. I said it's less than or equal to star. The key difficulties in wild ramification come in showing that this upper bound that we get on the number of components is less than or equal to the discriminant bonus. So wild ramification causes trouble here. It took us a while, but we figured this out. So I think I'd like to stop. How am I doing on time? Looks like I'm already over time. I just want to draw a nice picture to say what the shape of this upper bound is. What is the bound in terms of? I didn't tell you anything about MacLean valuations. I feel a little bad, but there's some really fun non-Archimedean geometry that goes into this. So if I can have 2 minutes, I would like to set that up. Is that okay, Daniel?
Yeah, that's fine.
Okay, so so the question is, what is this upper bound star? What does it depend on? I said it's explicit. So let me tell you what it depends on. So for this, we're going to keep things simple. Let's assume that f is an irreducible polynomial with a root alpha. I'm going to do an example on this side so that you can keep these things concrete. Let's say alpha is this element 3 to the 2/3 plus 3 to the 101, some huge number 101 over 6 over Q3, right? F is some degree 6 polynomial, the minimal polynomial of alpha. The key thing that shows up in these bounds is a lower degree polynomial. It's the minimal polynomial for a closest lower degree approximant. Okay, so I'm going to put this in quotes. I show you what it is in an example. Right. So in this example, you have this degree 6 element, but it's fairly theoretically close to a lower degree element, namely 3 to the 2/3. Right. And this phi is the minimal polynomial of 3 to the 2/3. That's easy to write down, which is x cubed minus 3 squared, right? And this is not well defined. There's no unique lower degree approximant. You can add any large power of 3 to this beta, and you get another lower degree approximant. But what matters is the degree, right? So there's a nice, not rigid picture to to see what this beta really means, right? So let me draw that for you first. So let's say we're going to start growing disks about this root alpha of f, right? So you have various p-adic disks. So the disk that matters to us here is this d prime. It's going to be all of those elements in k bar that are triadically at distance 101/6, right? Triadically close to alpha, right? So my beta sits somewhere on the boundary of this disk. The point is, if you're really close to alpha, imagine you start with a disk of radius 0 and you start growing this disk. Initially, there are no elements of lower degree in this disk, right? Initially, this really small disk about alpha has 6 conjugate disks. What does that mean? It means that every element in this disk has at least 6 different conjugates, right? There are no lower degree elements really close to alpha. So no lower degree elements here. But if you grow this disk, eventually at some point you're going to start trapping lower degree elements. So you get 3 to the 2/3 exactly when you're at distance 101/6 in this example, and you grow the disk even more, right? There's an even larger disk that contains 0. Maybe I should say it's even easier to see that there can be no rational numbers inside. Every element of k is at distance at least valuation of alpha away from A, right? So d double prime, this larger disk, is when instead of 101/6, you have valuation of alpha, right? So the same stuff. So you start at alpha, you start growing a triadic disk. At some point, you trap a lower degree element, right? And that's the beta that shows up here. And okay, so beta itself is not well defined. There are many elements of lower degree in that disk, but what is well defined is its degree. And what matters to us is the ratio of the degrees of f and phi. And lastly, the last parameter is exactly how far away this is. So you plug in alpha into phi, right? So in this example, the ratio of the degrees, degree 6 over degree 3 is 2, and lambda is vk of alpha cubed minus 3 squared. Alpha was 3 to the 2/3 plus a large power of 3, right? You can work this out. And the shape of our bound star, at least when E is at least 3, degree phi at least 2. I'm not writing the most general thing, but there is such a formula general. You get twice the floor of degree phi lambda plus E minus 1. Okay, so that's the kind of upper bound you get from McLean valuations, and you can show that this is less than or equal to the discriminant bonus. It's hard to do this in general because these lower degree approximations, when you're widely ramified, the field extension generated by phi might be nearly disjoint from the field generated by f. So it's really hard to compute discriminants of these field extensions, but we made it work. Sorry for going so much over, but that's all I had to say. Thanks.
Let's thank Padma for that great talk. You can unmute yourself and clap, or just click the clap button. Some people have even been clapping since the end of Wanlin's talk, so they were clapping through your entire talk. All right, so we're running a little over, and I don't want to go too over because I think some people might be logging in for specific talks, but maybe we have time for a couple questions. So does anyone want to raise their hand and ask a question? All right, I have a quick question. So you proved, maybe the answer is kind of implicit in your proof, but you proved some inequality between 2 numbers, or in fact 3 numbers. Yeah, the star, and some positive numbers, which are the differences of those. And I was wondering if those have any nice like geometric interpretations.
So we did a bunch of coarse things where the actual first upper bound that you get is bad. We massaged it to have this really nice shape, so it's hard to keep track of exactly what this is. And it's an open question in general how to explicitly describe the difference of these 2 invariants. But when the extension when f is tame, I can give a fairly geometric description of where this difference comes from. And it's where you look at this simple example, say y squared is x minus p, x minus 2p, x minus 3p, right? Let's say p is some large prime, x minus 100p, right? And maybe you have some other terms that don't reduce to 0. On the conductor side, this whole thing, all these roots coming together to order 1, this is something you can resolve using one blow-up, right? So on the conductor side, the calculation, the difference in the Euler characteristics is you just need one blow-up, you end up getting 2. But on the discriminant side, the discriminant keeps track of not just how many blow-ups you need to do, but it also keeps track of the number of roots reducing to 0, right? So in this case, you get twice 100 choose 2. And in this case, it's really straightforward to see where the difference in these two numbers comes from. It's just the fact that, you know, n times n minus 1 is at least 2. But and this is something you can spell out concretely in the tame case. I did this in this other argument in my paper. Unfortunately, the argument we have in our paper, which is now 70 pages long, we did a whole bunch of simplifications to write down this upper bound and lower bound nicely. So it's hard to keep track of equality, but Andrew said that at some point, if he has a graduate student, we'd give it to him to figure out exactly where we figure out exactly when equality holds in every stage. But you should think that the discriminant keeps track of also the number of roots in each cluster and not just how many blow-ups do you need to separate these roots.
And it looks like Yevgeny Zaitman has a question. Do you want to unmute yourself?
Yeah, what does happen in characteristic 2?
This construction of regular models breaks down. You can no longer produce a regular model. The two things that go wrong, this idea of getting a regular model of X by taking double cover of a regular model of P1 no longer works. Even if the roots of F have distinct reductions, the Weierstrass model is not regular. You get singularities at some random points. So that breaks, and you also don't have a similar nice description of the Swarm conductor, right? We use that 2 is different from the residue characteristic in this working definition of the Swarm conductor. So both of those go wrong. At some point, we want to think about this too. We don't know yet.
Well, and there was one more question asked in the Google Doc, which is whether you could post your notes on the Google Doc after your talk is done.
Sure, I'd be happy to. Thanks.
All right, let's thank Padma again then. If there are no more questions, you can also click the button again if you'd like. Great. So let's give people a little bit of time to get a coffee break. So let's reconvene in 7 minutes. So at 2:35 Eastern Standard Time for Hannah Larson's talk, and Hannah will be telling us then about Brill-Murder loci. Thank you so much, Padma.
Thank you.